Hello class, this is Ms. Riggins with today's video on section 7.2, integration by parts. As you're watching the video, please remember to write down important equations, formulas, examples, or statements. Feel free to pause, rewind, or replay the video as often as you need so you get a full and clear understanding of what's going on in the video. At the conclusion of watching the video, write a brief summary about the video in your notes and submit that summary as well as the top question via the online WISC form. All right, let's begin. We're going to learn a very important method, strategy of integrating functions you call integration by parts. If you recall in the previous video, we were able to integrate something by using the substitution method, which was based off the chain rule for differentiating functions, or a product of function, composition of functions. Today's strategy is integration by parts, and it's based off the product rule of differentiating functions that are the product of two things. So let's look at an example. As you can see here, this looks like something we would maybe try the substitution method with, but as we can see here, that the derivative of an inside function is not x, if we were to let x be the inside function. So we can't really use substitution method in this scenario. So how will we be able to find it? Well, let's say, for example, that we do want to think of a product, that this is the result of the product rule of some differentiation. So let's come up with an example. Let's say, for example, that we're looking at the product differentiating x e to the x. Well, using the product rule, that would be the derivative of the first times the second plus the second times the derivative of the first. And we end up with something that looks like this. Unfortunately, our integrand is not x to the ex plus e to the x, it's just x to the ex. So the question is, how can we get whatever we're differentiating to look like this? Well, if only that e to the x wasn't in the way, we'd be finished. So here's an idea. Let's differentiate the term x to the e to the x minus e to the x. So we get the same as before, but then we end up with x to the e to the x, okay? Which is exactly what we want. So we just happened to look up on the idea and ended up with the correct answer so that we can say that the antiderivative of x to the e to the x is equal to x times e to the x minus e to the x plus c. We actually ended up looking up on that spot, okay? So in order to do that, is there a more formal way we can go about doing that? And yes, and it's called a method that we're about to use called integration by parts. Here's what the integration by parts looks like. If I want to use the product rule to differentiate the product of these two functions, as you can see here, that's the product rule. If I just solve for u prime v in this equation, I end up with something that looks like this. And then if I were to integrate both sides of my equation by just simply doing the integral symbol, integrating both sides, and adding a dx, and adding a dx, sorry, I end up with something that looks like this. And that gives us a hint for what integration by parts does. So instead of here starting with the product and then differentiating, we're going to start with the result of differentiating and work our way backwards. And this is what it looks like. It's all nice and simplified. And the integration by parts says the integral of uv prime dx is equal to uv minus the integral of u prime v dx. And I know some of you are like, that doesn't look any more simpler, but trust me, it is. And when I was growing up, well, my teacher taught me even an easier way to say uv minus v du. And of course, we put an integral over here for this right hand side. So either which way they will both work, because u prime is du divided by dx, and so when I multiply by this, anyway, you guys get the idea. So, but your book uses this format. So let's go back to our previous problem and see if we can use integration by parts. In order to use integration by parts, you need to identify what is going to be u and what is going to be v prime, okay? Of your original problem. So in this case, we're going to let u be equal to x and v prime be equal to e to the x. Okay? Well, using integration by parts, then that means that I need to determine what, if v prime is e to the x, what is v? Well, we know that to be, e to the x is its own derivative, so we know that v is equal to e to the x. So that way, we have this expression. Sorry. We have this part. Oh, a different color. This part is now this part minus the integral of u prime, which since u is x, then du dx is 1. V, since we already said, we're repeating v again, dx. Okay? I know some of you are saying, wow, that looks a little bit more, it's still a difficult process, but wait. We end up with the integral of e to the x dx, which we know to be just e to the x. So I can simplify this by saying x times e to the x minus e to the x plus c is my answer. Voila, integration by parts. Now, I know some of you are saying, oh, but it's going to get more difficult than that. You're absolutely right. It will, but that's just the basis. We have to identify of our integral what is going to be our u and what is going to be our v prime. Then we're going to have to figure out what our v is and then plug it into this expression. Excuse me. The only concern is you have to be careful what you pick to be u and what you pick to be dv, because if you pick wrong, you may end up with a more difficult problem than you started with. So what if in the previous problem we had picked, instead of u being x, we had picked u to be e to the x, and therefore v prime being x. If we had done that, then we would ended up with u v, because v prime is x, so v must be x squared over 2, minus integral of u prime, which is e to the x, times d times v, which is x squared over 2. Sorry. Well, is nice and lovely like we would prefer. So in this case, that would have made it even more difficult integral. And you should stop there because you're not going to get an even easier problem. And the rule of thumb is if this integral is worse than the original integral, then you've picked the wrong u and v. I can't say that enough. So sometimes you may start the wrong way and then have to retrace your steps and start back again. But that's part of the process. Here's some suggestions about how to choose u and v prime. First and foremost, whatever v prime is, you need to be able to find v, i.e. the integral of v prime. So it helps if u prime is simpler than u, and it helps if v is simpler than u prime. I know you're saying, well, huh? Well, at least not as complicated as well. So let's take a look at some other examples, and then we'll get the hang of it, okay? Because only practice will get the hang of it. So in this case, I want to evaluate the definite integral from 2 to 3 of natural log of x. Well, we don't know, it's not an elementary integral, so we don't have the integral antiderivative natural log of x. But what we can do is to use integration by parts. Here's a trick. Natural log of x can be represented as u times natural log of x. So I'm going to let u be equal to natural log of x and let dv be equal to 1 times dx. Okay? So now I can replace this with my u, and then dv right here. Oops, right here. Okay? And so then using integration by parts, I need to determine du dx, which is easy. It's 1 over x. That's a popular integral. And then the integral of dx, which is just x. And so I have this statement right here. So I have u times v minus the integral of u prime, v. And because we started with the limits of integration from 2 to 3, we end with the limits of, we still maintain that, okay? And the great thing about that is, look, these two things seem to cancel each other right out, which is exactly what we love. So we end up with an even simpler problem because the integral of dx is just x. And so now we have to evaluate this, and then we're done. Ah, isn't that lovely? Great. Now, of course, not everything will work out right. And since it's past 10 minutes, I'm going to show you a more challenging problem just so you can see a strategy to approach that. X squared sine 4x dx. Okay, well, initially you're going to say, well, let u be equal to sine 4x and dv be equal to x squared dx. Thus, you're going to have this scenario going on for u prime and v. But as you can see, this is a lot more difficult than what we wanted, what we started off with, because if I multiply these two together, I just have a more difficult expression in this. So let me switch that. Let me let u be equal to x squared, and let me let dv be equal to sine 4x dx. That means that u prime is 2x and v is equal to negative 1/4 cosine 4x. Still not as not a lovely simple part, but it's a lot more easy to integrate. It's a lot easier thing to integrate from here. I mean, to integrate this compared to that, okay? And that's why we like that. So let's go ahead and do that. I know you're saying, but we're still not going to get our answer. Patience, grasshopper, we will. So using this, I end up with this. And then I end up with this. So like I said, we will still get something involving x and cosine 4x. Now the question is, well, man, I'm still not finished because I don't know how to integrate this. Well, you've made progress because this to integrate is a lot easier to integrate than this, okay? Well, if you were to integrate it. So let's go ahead and do another integration by parts, okay? So in this case, we're going to let u be equal to x and dv equal cosine 4x, and that means that u prime is 1 and v is 1/4 sine of 4x. So just for this part alone, and we're only doing this part, so we have, let me move this up so you can see. We have this, and we're going to apply the integration by parts just for this piece right here. And we end up, and this is really lovely, we end up, because we can easily integrate sine of 4x, using elementary integrals, and we end up with this part. So this is what this part is. And so now we can plug this part back into this part. And when we do that, we end up with negative 1/4 x squared cosine 4x plus 1/4 sine 4x plus cosine 4x plus c, okay? And that's what this looks like right here. Okay. And then we have our answer. Lovely, isn't it? Yeah, it is. Another strategy. So, but going back to here, sometimes you're going to have to integrate more by parts, apply it more than once. But as long as each time you're getting a simpler integral than before, then that means you're making progress, and that's ideal. Very quickly, this situation, cosine squared theta d theta. Let u equals cosine theta and dv equals cosine theta dx, and then therefore we have this as our u prime v. We plug it in, we get something that looks like this, and some of you are saying, well, this is the same thing, if not the same level, cosine squared sine squared. But let's just think about that. Here's a trick. Cosine, we're already dealing with cosine squared theta. Using the trigonometric Pythagorean identity, we can represent sine squared theta as 1 minus cosine squared theta, okay? And then separate the integrals. And then we end up with, oops, I need to really move this up. We end up with cosine theta, sine theta plus theta. Oops, sorry. So end up with something like this, which is the result of this. But then we say, look, we end up with another cosine squared theta. Well, we started off with a cosine squared theta and an integral of cosine squared theta. So let's just add cosine squared theta to both sides. So now we have 2 cosine squared theta equal to what's left. And what's left is essentially this. And I know what this is. Cosine theta sine theta plus theta. And then I divide it by 2. So I get 1/2 cosine theta sine theta plus 1/2 theta plus c. And that's my answer. So sometimes if you end up back at the same thing, you can use that to your advantage. All right, that's it.